So welcome to the VaNTAGe seminar, and we are continuing our series of talks on rational points on higher genus curves and the Chabauty method. And today we're very happy to have Aashraya Jha speaking about quadratic Chabauty over number fields. And is it all right to record this talk, Ash?
Yeah, absolutely.
Wonderful. And please ask questions during the talk. So
Yeah,
please go ahead.
okay. Amazing. I want to thank the organizers for inviting me to give a talk here. It's really lovely to be here, and I would like to thank everyone who's come to see this. Okay, so let's start. My talk's about quadratic Chabauty over number fields. I had a rather verbose title on the VaNTAGe website. It's about rational points beyond the rational numbers. And I just want to give number fields their due credits. There are number fields aside from the rationals, and I think we should study them as well. Okay, so our story starts with a classical classification problem, which is the following. So our setup is that we have an elliptic curve or a number field, okay? And by the Mordell-Weil theorem, we know this is a finitely generated abelian group. So it's isomorphic to z to the r plus a finite abelian group, which I'm calling ek tau. And what we will be interested in today is ek tau, and also actually ek bar tau, where k bar is the algebraic closure of k. And one of the great theorems of the 20th century was Maser classifying what ek tau is in the case where k is equal to q. And there has been further work for k in quadratic fields and cubic fields. I think some work has also been done for quartic fields now. And the strategy of the proof is to determine q points on modular curves, x1 of n for all n. These parameterize elliptic curves with a marked n torsion point. Okay, so we have this sort of really nice geometric view. There's also a more Gawa representation view of the following. So this ENK bar as an abelian group is isomorphic to Z mod NZ squared, but it also has the structure of a Gawa module. Here GK denotes the absolute Gawa group of K. So we get this representation, this two-dimensional Gawa representation. And I'll call this row E comma N, and I'll let the image be HN. So one example, which people are usually familiar with, is the following. So say I do have a point of order n, which is k rational. Then for any Gawa automorphism, this point is fixed. So we get Hn will be of this form, where you'll have a 1 on the top and 0 at the bottom in the left column. This is obviously dependent on a choice of basis here. So it will be conjugate to this. And what one might want to think of is gamma 1 of n, the usual modular group. So let's sort of look at other subgroups of GL2 Z mod NZ. So say we have one of these. We'll say an elliptic curve E has H level structure if there is a twist whose image is inside H up to conjugation. And there are subtleties here, and I'll refer people to the paper of Rouse and Zurich Brown, where they sort of discuss this in detail and discuss what can go wrong in positive characteristic and if you have extra automorphisms. So we have such a subgroup now. Now this curve is a compact curve, XH, and it will parameterize these elliptic curves with level structure H. And I'll call it the modular curve of level H. And so x1 of n, which we saw earlier, is a special example of this phenomenon. And xn, which sometimes people call the big modular curve, corresponds to H being the identity. And this parameterizes a pair, E and P and Q, which generate your n torsion, along with an isomorphism with Z mod NZ squared. And if people are more familiar with Shimura's definition, then I'll remark that XH is equal to this quotient. One has to be slightly careful about if you're considering a right or left action. So then there's stuff with transpose of groups. I'm sure the experts know this. And in this talk, every group I'll consider will be equal to its transpose group. So there'll be no problems. Okay, any questions so far? Okay, I'll move on. So
Sounds great.
yeah, your modular curves. So we were considering the torsion n for some specific n. And a natural thing to do is like consider it for all n together. And the natural way of doing this is by taking a projective limit of your n torsions. And one then gets this adelic representation. And Serre proved in 1972 that if E does not have Cm, then this image has finite index in GL2Z hat, which is isomorphic to this direct product of all the p-adics. And then following Mazur's work on rational points on x1 of n, he asked the following question. So he takes a subgroup H of GL2Z hat, and he asks which elliptic curves have associated Gauer representation, which maps into this H. And this should be up to conjugation. And this is a really hard question, but we can make this a bit easier. It's still a hard problem, but what we can do is project to one of the GL2ZPs, which I'm going to call L. This is following Rousseau and Zurich Brown L-adic images. And this is like a vertical analog. So we just sort of look at prime by prime. So what do we know so far? So for elliptical curves over the rationals, Rouse and Zurich Brown classified L-adic images for L is equal to 2. And we also know the classification for 13 and 17. So this follows the paper of Rouse and Zurich Brown, where they document a lot of cases that have been done. And I think this was eventually finished off in a paper of Balakrishnan, Dogra, Teutmann, Wonk, and Euler. Okay, there's more, or we have more than 3 primes, right? So Russell and Zurich Brown compute a lot of L-adic images for L is less than or equal to 37, and do actually suggest a classification for all L. And it's conjectured that this L-adic image is surjective for all L greater than 37. And there's strong evidence to this due to work of Furio and Lombardo most recently. There has been a lot of other work as well, but I think this is the most recent. And what Furio and Lombardo show is that this image is either surjective, the map is either surjective, or the image is the extended non-split Cartan subgroup, which I'll talk about in a bit. And I'd like to remind everyone that the way this classification is working is by finding rational, it's equivalent to finding rational points on modular curves. So it's a naturally interesting question to find rational points on modular curves. Okay, so let's discuss non-split Cartan. So here I'm giving you a very group theoretic definition. So I'll let O be the unique unramified extension of ZL. And I'll choose a unit, A, and I'll multiply by it. And then I get this ZL linear map, which induces an injection of O cross into GL2ZL. And this induces a further map on the quotients. And the image is called non-split Cartan. And the idea here is that, of course, we can have a lot of generators, but they'll all be conjugate. All these subgroups will be conjugate to each other. And there's also a natural involution on O, and I'll call this involution iota. And then the extended non-split Cartan subgroup, which I'm denoting with the NS plus, is generated by the non-split Cartan and iota. And the curve which will be important for us will be X non-split Cartan of L to the E for some prime L and E some positive integer. I now want to highlight this fact where Mazur's proof is remarkable, but it doesn't work for us. uh, because he crucially uses a rank zero quotient, the Eisenstein quotient, of the Jacobian of x naught of n. And one doesn't have such a quotient for non-split cation. And non-split cation, I've sort of described it group theoretically, but there is a really nice geometric description due to Reboledo and Wootrich. And I'll try and explain it here. So remember, we had to choose a generator of O cross, and then we like take a quotient. So I'm letting H be the image of a generator of FL squared cross. And for L torsion, it's isomorphic to Z mod L squared. And then we can sort of look at all the subgroups of cardinality L. And we have exactly L plus one of these. And the idea is the image of this generator will just sort of transitively permute these subgroups. And then we have this definition of an H-oriented necklace. And what's happening is that you have a list of all these subgroups, and H just sort of permutes it to the next one. It just shifts it by one. So a picture is worth 1,000 words. So what's happening is you have this arrow, and C0 goes to C1, C1 goes to C2, etc. And CL will go back to C0. Okay, so the technical point is that if H prime is another generator, then there is a bijection between H-oriented necklaces and H prime-oriented necklaces. And there's this natural involution where you just like sort of reverse the order of C0 through CL. And so you go from CL, you're sort of identifying C0 through CL with CL through C0. And so this is an H-oriented necklace, which looks almost identical, but if you paid some attention, I have very cleverly removed the arrows from this picture. So yeah, so the arrows were denoting the orientation. And now the theorem of Reboledo and Wootrich. So the non-split Cartan curve parametrizes curves E with an oriented necklace, and the extended non-split Cartan curve parametrizes elliptic curves with a necklace. Okay, any questions about what this curve is? Because this will sort of end up being the main object of study.
So are the lengths of these necklaces always L plus one?
Yeah, exactly, because we want all the subgroups of Z mod L squared, which have cardinality L. Yeah, good question. Are there any other questions? Okay, I'll move on for now. So we'll be interested in X non-split plus 27. So after the work of Rausen and Zurich-Brown, the classification for L is equal to 3 was almost complete. And the only sort of curve left to determine rational points on was non-split plus 27. And this is a huge curve. It has genus equal to 12. The rank of its model Way group over the rationals is also 12. And the paper of Russell and Zurich-Brown is really great. They use a lot of different techniques to find rational points on a variety of curves, modular curves. But this was sort of resistant to their methods. They do determine 8 CM points on this curve, but we don't know if these are all of them. Okay, so this is the main theorem for today, that these 8 CM points are exactly all the rational points of this curve. And so this finishes off the triadic classification of Gawa images of elliptic curves over the rational numbers. And they have a really nice table which lists all the subgroups, and you can go check it out. It's really great. We know everything. We have boxes. We had boxes for torsion, and now we have boxes for triadic representations. Just want to put stuff in boxes and be happy with that. Okay, so how do we do this? How did we manage to figure out that these were the only points. So in their paper, Reisler and Zurich-Brown determine a genus 3 quotient of a Q zeta 3. So here's where number fields come in, right? And the Jacobian has model way rank 6 over Q zeta 3, and they determine 13 points. So what we can do, because we have this map between x naught plus 27 and x, we can just pull back points. So it's sufficient to compute the Q zeta 3 points of x. Okay, so how do we do that? So this is what the rest of the talk will be about. Yeah, before I go on, are there any questions about what the main goal of this talk is? Okay, I'll move on then. So all the methods discussed in this talk are p-adic in nature. So let's get on. Here's some setup. K will again be a number field. It'll have degree D, and we'll let x over k be a nice curve. So that's smooth, projective, geometrically integral. And its genus will be g greater than or equal to 2. We'll fix a rational prime p, which splits totally in k, and we'll assume at all places above p, x has good reduction. I'll also use these psi i's to denote these embeddings into qp of k. We'll have exactly d of them because p splits totally. And if j is I'll let j be the Jacobian, and I'll let the rank of j be r over k. And I'll also assume, this is vital, that I have a rational point, and I'll embed the curve inside the Jacobian via the Abel-Jacobi map. Okay, so Jen talked about this, and I'll just quickly go through this again. There's this method of Chabauty and Coleman, where what one is doing is you look at this p-adic manifold JQP, and you look at smaller dimensional manifolds XQP, which has dimension 1, and the closure of JQ, which has dimension R. So if R is less than G, then R plus 1 is less than equal to G. And then due to like an unlikely intersection principle, you don't actually expect infinitely many points because the codimension sort of is too small. And Chabauty exactly shows this. So he shows that this set B here is finite. And this was made a bit more effective by Coleman using his Coleman integrals, where he develops this theory of integration and shows that if R is less than G, using linear algebra essentially, you can find a vanishing functional on the Jacobian, and then you can, which vanishes on the Q rational points. And then you can pull this back to XQP using the Abel-Jacobi map, and you get a non-zero locally analytic function, which vanishes exactly on, it vanishes on the rational points. There might be some spurious points, but the point is that rho is locally analytic. So by Weierstrass preparation theorem, the preimage of 0 will be a finite set, and it'll contain the rational points. And then you can use model-way sieving and other methods to isolate the rational points exactly. So Nathan sort of brought our attention to full fat quadratic Chabauty. So today I'll just stick to skim quadratic Chabauty. Maybe the number fields add some other flavor like chocolate, if you like that. But here is the hypothesis. Say these p-adic vector spaces of the model way group of J and the functionals on the one forms, on the holomorphic one forms, are isomorphic to each other. And this implies R is equal to G. So we are outside the condition where Chabauty works, Chabauty-Coleman works. And we assume there exists a nice correspondence, Z, of x times x. I'll not define nice right now. I will say that it does not mean nice in the sense of nice curve. It's a bit more technical. I'll give you a hint of what it corresponds to in a bit, but for now there's some correspondences which are nice, and we need them to exist. So Balakrishnan and Dogra show that there's a non-constant locally analytic function, which is obtained from a p-adic height. and a finite set T, so such that this locally analytic function, it sends the rational points inside T. And now the preimage will be finite again and will contain the rational points. So this is rather nice. And this is an artist rendition. Obviously, this is completely wrong because the p-adic numbers are totally disconnected, but you can imagine these red points are the points in the preimage of T. Okay. I want to mention like why quadratic Chabauty is actually quite good at computing points of modular curves. So if I have a modular curve and its Jacobian is Q simple, then we have R will be a multiple of G. And this basically follows from the fact that it's a GL2 type variety. So the endomorphism ring will have rank equal to G, and then the model way group is a endomorphism ring module. So if R is not equal to 0, Chabauty-Coleman won't apply directly to this curve. There are like a lot of methods to use Chabauty-Coleman in conjunction with other methods, but it doesn't apply directly. But quadratic Chabauty does. Remember, we needed this R is equal to G condition, and this is sort of satisfied here. And we also needed this nice correspondence. But modular curves have a lot of correspondences. This is really nice. And we can actually compute them very explicitly. We have these Hecke correspondences, and we can sort of compute with them using Eichler-Shimura and a host of other techniques. And Jen gave us a lot of modular curves on which points were found using quadratic Chabauty. I won't go through the list again, but I'll just highlight that I think the highest genus that was worked out was G is equal to 6, which is also quite remarkable. I think that's a very high genus to have worked with. Okay. Now I want to come to the number fields part. So Sixsec first tried this based on a suggestion by Weatherall, where now instead of just considering one functional, because you're working over a number field K, you look at these psi j's and they give you different functionals to work with. And we get dg of them. And then we can pull them back again and then extend to the whole p-adic manifold. I'd like to point out this x k tensor qp is d-dimensional. And so Weierstrass preparation doesn't work the same way. And so we'll need at least d functions. And then we'll need to look at their vanishing loci together and hope that this intersection is finite. And if you do some inequalities, you work out that R should be less than equal to D times G minus 1. To convince you that this is not absurd, you can consider the case where D is equal to 1. So R is less than equal to G minus 1, which is equivalent to R is less than G. And Sixsec uses this method to compute the points of a generalized Fermat equation. And he considers a lot of quotient curves and uses this Chabauty-Coleman over number fields to work out their not rational points over some number field. Okay. I now want to talk about quadratic Chabauty over number fields. So we'll have a similar assumption of this isomorphism between the mod Way group and the functionals on the one forms, both of them tensored with QP. On the left, we know this dimension will be R. On the right, this H naught X gamma omega 1, this has K dimension G, but over Q, this becomes DG. And that's why the dimension on the right is D times G, not just G. Okay, so yeah, I should have probably told you what I'm tensoring over. So I'm tensoring over Q here. So again, as before, we need D p-adic heights from which we'll obtain these rho i's and finite set TEIs. And we'll want the image of the K points to lie inside these TIs. And then we'll consider the intersection of these pre-images. And for sure, that we'll know that the rational points lies inside this set P, which I've defined here. So here is what one might want to consider. So both of these blue lines denote the preimage of some finite set. So right now we are in a surface because I'm considering a quadratic field. So the dimension is 2. And each of the preimages will correspond to sort of a curve inside the surface. Okay, so this looks nice. It looks pretty similar. Yeah, you've got two curves, so they should intersect in finitely many points. Okay, this is false. For example, look at these functions, f1 and f2. These functions are not algebraically dependent. They don't have like any nice relationship between them, but they vanish on the diagonal. So the vanishing locus has infinitely many points. So this is bad. This can happen. And so the analysis for finiteness is rather hard over number fields. But one can still compute this set B, which I was talking about here, and we'll still have the rational points inside B. Okay, what does it mean to compute an infinite set? Then we have a problem. But if it's finite, then this method is still quite good to determine the rational points. Okay, with that caveat, let's figure out how do we get these row i's. So I told you they come from these p-adic heights. So Jen talked about these two in her talk. I'll mention these again. The first thing is like I can take points from X, and we have this Étale-Abel-Jacobi map, which takes them inside the Jacobian and then puts them inside the dual of the one forms. And what Nekovar does is that he defines a family of p-adic heights, which depend on a choice of an Idel class character. So this is just a continuous additive homomorphism. And splittings of the Hodge filtration of the de Rham cohomology. And one sort of important point is that H decomposes into local heights, just like the Néron-Tate height. So here, I haven't told you how many Del class characters one has, but for example, for imaginary quadratic fields, we do have two. So while there's one Néron-Tate height, there could be several p-adic heights for just one prime. Okay, I think I've gone through a lot. Any questions? Okay, I'm going to move on. So how do we get to this row? So Balakrishnan and Dogra construct this element, which I'll call AX, inside this sort of functional space of the one forms. And this AX corresponds to this divisor X minus B and this Chow-Heegner cycle, DZBX. We won't really go into how we construct this because it's quite technical, but it is sort of important in other aspects of arithmetic geometry as well. And so we now fix an Idel class character in a splitting of Hodge filtration, and we let H be the corresponding height. Your function rho will be the difference of my global height H and the local heights at primes above P. And an important point is that we can actually extend this to the whole p-adic manifold. We first sort of computed on the k points, but we can extend it to the whole p-adic manifold. And Balakrishnan and Dogra show that this the complement of that function, remember the height was a sum of local heights. So if we like look at the heights at places not dividing P, the sum of those is finite. And the way one sort of gets this is that if you have potentially good reduction, then your height is identically zero. So for most places, your height is identically zero. And for the places where you have where you don't have potentially good reduction, it still takes finitely many values. So now we get that this function rho sends the rational points to T. And we'll call this rho comma t a quadratic Chabauty pair. And over the rational numbers, the preimage will be finite, and we can identify the rational points inside this preimage. For example, using model way sieving, if we have additional points, sometimes you just get exactly the set of rational points, and then you don't have to do any more work. Okay, so what happens with number fields? So it becomes a bit more tedious, because remember now, our number field has degree d, so we need d functions. So how do we get them? We'll try and get everything we can. Oh, there's a typo here. This should say RNS -1 in the second bullet point. But okay, how do we get these d heights? If we take the rank of Néron-Severi, then we get RNS -1 linearly independent correspondences, which will each sort of give us a family of p-adic heights. And if we let R2 be the number of complex places, then we'll get R2 plus 1 linearly independent Idel class characters. So we expect this due to Leopold's conjecture, and this has been proven for abelian extensions. So for a number field K, we expect R2 plus 1 times RNS -1 p-adic heights. And the thing we want to compute is the intersection of all these pre-images. So, and hope that this is finite. Okay, I'll highlight some results which are known about finiteness. So Sixek observes for Chabauty-Coleman over number fields that, say I have a curve C over L, where this rank hypothesis is contradicted. So RL, this should be strictly greater than, sorry about that, that's a typo. If RL is strictly greater than DL times GL -1, then for any extension K over L, the Chabauty-Coleman locus for C base change to K will still be infinite, even if CK satisfies the required bound. Okay, so this is a sort of a silly example, but what if you remove this condition? So Dogra actually exhibits a curve where for all subfields of K, the rank hypothesis is satisfied, but the Chabauty-Coleman locus is still infinite. And the way he does this is that he constructs a quotient of this curve where this rank hypothesis is not satisfied. So one has to be really careful. Like you can get a lot of different behaviors where you do get infinitely many p-adic points in the vanishing loci. We do have a positive result, which is the following. So what do I mean by these symbols, jk bar sigma I? I mean, I take the base change of J to the algebraic closure using a certain embedding, sigma I of k bar into C, where C is the complex numbers. So if this is basically saying if I take two different embeddings of the Jacobian after base changing, these shouldn't have any common isogeny factors. So if this is true, and then we have the right rank bounds, then the Chabauty-Coleman locus and quadratic Chabauty locus are finite. Okay, again, I didn't write the exact technical statement that Dogra proves. This is not strictly true. What you can deduce is that the rational points will be finite in this case, but it is not actually true that he proves that the loci themselves are finite. There's like a portion of the loci which is finite, but that portion contains the rational points. So this is not technically true, but it was hard to sort of fit the whole statement here. And Daniel Haas and Nicholas Triantaflou have also worked on this restriction of scalars number fields method. Okay, any questions? So the idea is that over number fields, it is hard to prove finiteness. But it is still true that we can compute things. So there's this really nice paper of Balakrishnan, Besser, Bianchi, and Mueller, where they compute the integral points of hyperelliptic curves over number fields and the rational points of bielliptic curves. Bianchi computes the z zeta 3 points of the elliptic curve y squared is equal to x cubed minus 4 using this method. I extended this to non-base changed elliptic curves where you get some subtle behaviors when the curve is not a base change. And Gajowicz and Mueller compute the z square root 7 points of an even model hyperelliptic curve using this method. I'll highlight that in the first bullet point, like all the number fields were either quadratic imaginary or quadratic real. So like they're all quadratic. I don't think there's been worked on over high degree number fields. Okay, any questions before I move on? Okay, I'm gonna move on then. So let's come back to the meat of today's talk, classifying these triadic images. So recall that this curve was large. It had rank equal to genus equal to 12. And this is too large for quadratic Chabauty to really work. There's a lot of action of Frobenius which need to be computed, and I think that is infeasible for such a large curve. What else can one do? One could try and look at x non-split plus 9 and pull back points, but one can't do this because that curve has infinitely many points. And Rouse-Sutherland and Zurich-Brown noticed that there are no intermediate subgroups between non-split plus 9 and non-split plus 27. But there is one when you intersect these with this subgroup D that I've written here. This D, the modular interpretation of this D is that I'm going to choose two generators of 27 torsion, and I'll take the wave pairing. And when I look at it mod 3, it should be 1. So this is like a sort of wave pairing condition. So we can look at the modular curve corresponding to this subgroup H. And XH has genus 3, and it's naturally defined over Q zeta 3, and it is a smooth plate quartic. And Rouse-Sutherland and Zurich-Brown actually compute a really nice model with really small coefficients for this curve. And I'll let J be the Jacobian of this curve, as before. And this condition, which I alluded to earlier about the Mordell-Weil group tensor QP being isomorphic to the functionals on one forms tensor QP, does hold here. So this is quite nice. It falls in our purview. So R is equal to 2G. Remember, D is equal to 2 because Q zeta 3 is a degree 2 extension. But we can't use quadratic Chabauty directly here. So what do we do? I'll tell you about nice correspondences now. So nice correspondences are in bijection with trace 0, Rosati fixed endomorphisms of J. In this case, the Rosati fixed endomorphisms are isomorphic to Z zeta 9 plus, the maximal real subfield of Z zeta 9. And so if you take the trace 0 bits, so the dimension of Z zeta 9 over Z is 3. So if you take the trace 0 bits, you'll be left with a dimension 2 ring over Z. So there exists two linearly independent correspondences. And so there's at least one, obviously. X has bad reduction at the prime above 3. And that's the only place which maybe you expect, because this is sort of a quotient of this level 27 curve. And for K, an imaginary quadratic number field, we have two Edel class characters, as I mentioned earlier. And these are called the cyclotomic and the anti-cyclotomic Edel class characters. They sort of, what the Edel class characters are actually doing is that we remember we had these local heights. They sort of help us put them together. That's the role of Edel class characters. So again, we'll consider the rho chi as we did before, and the rational points will take values in this finite set, T chi. Okay, so in the setup, I wanted a prime that splits, and my curve needs to have good reduction at places above P. So 13 satisfies these conditions. So to compute this row, we need to compute HP. And there are algorithms for this developed by Balakrishnan, Dogra, Mueller, Teutmann, and Wonk. And these generalize to number fields quite readily. One has to be careful about identifying the completion of K at mathfrak P with QP, but most of the techniques generalize very readily. I'll point out that we need iterated Coleman integration and computing the action of Frobenius on this curve. And maybe a nice tidbit is that what we need this nice correspondence for is to compute its action on the de Rham cohomology of X. And we can use Eichler-Shimura for this. But this was like a really tedious process. I thought that Eichler-Shimura doesn't work because of how long it took. And once it finally worked, we noticed that the entries of this matrix had 48 decimal digits. But it does work. Everything's okay. So we have our function rho, and now we need to figure out this set T chi. Oh yeah, this is a part of my thesis. This is the appendix to my thesis. So I wasn't making up the 48-digit thing. You can like count them if you like, or you could go and see my thesis and see all the entries. Okay, so to compute T chi, we need this definition of dual graphs of curves. So graph, I need to tell you what the vertices are and what the edges are. So the vertices will be the irreducible components of the curve, and the edges will be the singular points. So my curve is no longer irreducible. So again, picture 1,000 words. So if I have a smooth curve, then the graph will just be a single point. My curve looks conspicuously like the letter C. If I have two P1s intersecting in 2 points, this is called a banana graph by Dogra and Betts. So you get the corresponding dual graph, which has been conveniently colored in yellow. And the graph we'll actually care about is the special fiber of the minimal stable model of our curve at the completion of K at the ramified prime above 3. So it's got 4 components and it intersects transversely. One of them intersects transversely the other 3. So you get the following dual graph. So the green components go here and the blue components in the middle, and it intersects them at these red points. So these are the edges. These green components are elliptic curves, and the blue one is a P1. I'll discuss this in more detail in a bit. Okay, so why dual graphs? Because we have this theorem of Betts and Dogra. So if gamma x is the dual graph of the special fiber of a regular semi-stable model, they have a theorem that says the local height factors through this natural reduction map of xkv through gamma x. And by gamma x, I actually mean the vertices of gamma x, not the edges. And what we also get is that the height of the base point we can sort of fix to be 0. Okay, so what do we need to do now? If I can show that this reduction map is constant, then my local height at the place above 3 will just be trivial. And it is actually sufficient to show that gamma x has precisely one Galois covariant vertex. Gamma x is this curve defined over, comes from like a K3 thing, so it has a natural Galois action. And Oleo Sen computes a minimal regular model of this curve, and we determine the Galois action on the dual graph of this model. So how does one do this? One computes extension of K3, which I'll call L, and a model for P1 which I'll call script y, and I'll consider its normalization, which I'll call x prime, in the function field of my curve. And to compute y, Ole uses this correspondence between valuations and models. And the valuation he chooses corresponds to this degree 9 polynomial, which he computes explicitly. And the main sort of thing that makes this work tick is that we figure out that the Gawa group transitively permutes the roots of phi. And this is because phi is just irreducible. Okay, so what's going on? I'll try and show you a picture so that you can see what's going on. So this is the Berkovitz space of P1. If you don't know what that means, that's completely okay. I just want to use this picture. So these points D0, D1, D2, D3, they correspond to some valuations. And the model will sort of correspond to the filled in area here. The points at the bottom here, they correspond to the roots of phi. And because the Gawa group permutes these 9 points, it also permutes these 3 points, D1, D2, D3. But due to where like D0 lies, it doesn't permute that. That remains fixed because you can imagine this one going here. So that would send D1 to D2. But D0 just stays fixed. Okay, so what does this buy us? The way we are computing this gamma x prime is that we are taking the normalization in a function field. And what happens is this D1 is a rational component. All these 4 things are rational components. When I normalize, D0 remains a rational component, but D1, D2, and D3 become elliptic curves, E1, E2, and E3. And this map here is Gawa equivariant. But we know the only vertex on the right that is Gawa invariant is D0, which means the only vertex on the left that is Gawa invariant is D. So that's it. That helps us determine that the graph has just one invariant vertex. And therefore, this is what the sufficient condition was. This means this set T is 0 for any Idel class character. Any questions about this? Okay, I'll move on. So the last bit of this computation is the following. So as I mentioned before, we'll get 2 linearly independent correspondences corresponding to the trace 0 Rosati fixed endomorphisms of J. And these actually end up being really important. So we first compute the height on K rational points. And to extend it to K tensor QP, we actually make use of both of these correspondences. Then we use a multivariate Hensel computation we fix one of the correspondences, Z1, and we figure out this intersection here. And this set does contain points which are not in XK, but all of these spurious points aren't zeros when we compute the other locally analytic functions corresponding to the other nice correspondence. So then we have a theorem because we have the Q zeta 3 points of X. We have the rational points of X non-split plus 27, which was the goal. And as determined earlier, these all correspond to CM elliptic curves. And here's the proof. So yeah, this code is not optimized yet. It takes a long time. This computation took about 2.5 hours on my laptop. And it involved a lot of pre-computation as well. So this is also not completely accurate, but it works. We have a result. It's amazing. What do I want to do in the future? I think one interesting thing would be to like go curve shopping to find other curves which are quotients of modular curves over number fields. Because what this method sort of helped us do, it helped us trade genus for degree. We managed to get a lower genus curve, even though the degree was higher. But now we have a method to sort of combat the degree. And another more theoretical question I have is to find criteria for the finiteness of this pre-image of locally analytic functions. Because Dogra has this really nice result, but it is violated. His hypothesis is violated by a curve xh. And in fact, if you have a quotient of a modular curve, then the hypothesis of like the isogeny factors on the different embeddings not talking to each other will always be violated for modular curves. And modular curves are really important. We want to work with them. So I think it would be nice to prove something for modular curves, which is not covered by Dogra's result. And that's it. I want to thank you all for listening to me.
Thank you for that fantastic talk. So this is a great time for people to ask questions. Would anyone like to ask a question? Well, maybe I can start with one which is maybe not that hard, but the finding actually the CM points on these modular curves. Do you have a method to do that more generally?
I think there's work of Alvaro where he computes the image of the aládic images of elliptic curves. I know Drew, Jeremy, and David do this for non-CM curves, I thought. But I thought like Alvaro does this for CM elliptic curves. Could you correct me if I'm wrong, Drew?
Yeah, so in the modular curves database, which is on the beta section of the LMFDB, we use this. And so we use Alvaro's characterization of, we know exactly, given a CM discriminant, we know exactly what the image is going to look like. And then we can test whether that's a subgroup of H up to conjugacy in GL2Z hat or not. And so that gives you at least the J invariance of the CM curves. It takes it takes a little more care to get to make sure you account for multiplicities and get the number of points nailed down exactly. But the nice thing is you can do this sort of moduli theoretically. You don't need a model for the curve to figure out the CM points.
Oh, cool. Sam, how about you?
Hey Ash, I just had a question about back on slide 29, you had this subgroup D that suddenly appeared that allowed you to basically find an isogeny factor. I was just curious where this came from, and does it have like a nice moduli interpretation, or is there some way to explain it?
Yeah, so I tried to say this. What happens is that this D is basically a condition on the wave pair. So you choose two generators of 27 torsion, like an ordered pair of generators. And the wave pairing will go to zeta 27. But you can look at it like you can sort of project to mod zeta 3. And this is what that condition is about. And I've been told by Drew, Jeremy, and David that I think David noticed that this subgroup exists. I think this is a small number phenomenon. I think for higher level curves, like for bigger primes, one doesn't expect things like this to happen. This is, yeah. Does that make sense?
I think so. So like the geometric components of this are given by the values of the Vey pairing, and you're taking some like collection of those.
Yeah,
That's
exactly. So
okay.
over Q, so I can also, so this curve has a natural structure as a K scheme, where K is Q zeta 3. Over Q, this has two components. Like if I look at this as a curve over Q, and then I base change to Q bar, this would have two components. And yeah,
Okay, thank you.
yeah. Thanks for your question.
Would anyone else like to ask a question?
I might ask a question or make a comment. How's your curve shopping going?
Yeah, I was looking at your paper and trying to find things for L is equal to 5. And I think that is a bit hard, I realized. So I think Jeremy told me this, that one way of doing this is by computing a lot of Riemann-Roch spaces to see. Because there are all these sort of large genus curves, and what you're trying to do is see if there exists a quotient. So the first thing I did was go on the LMFDB and like do things on the level of abelian varieties. And some of them do have smaller dimensional isogeny factors. So I was like, okay, there might be a chance. Let's see what goes on. But there's no group theoretic reason for a curve to exist. And I talked to David Zyrina about this, and he was like, well, if there's no group theoretic reason, then maybe there doesn't exist one. I sort of did some Riemann-Roch computations and didn't come up with anything, but I think there's still, I plan to sort of do these computations for other primes and see if something hits.
Because the other thing that occurs to me is, I mean, identifying this subgroup D here was critical.
Yeah.
And I'm wondering if one could automate this process of looking for Ds that will let you find an intermediate curve where one shouldn't exist. Or,
Yeah, so I did
quotient.
this sort of thing for L is equal to 5 and L is equal to 7. I haven't done it for the other primes. So that doesn't exist. I can't do this for other subgroups, unfortunately. At least so like the quadratic Chabauty over number fields method right now only works over quadratic number fields. So there's no natural thing for quadratic number fields, I think. That's what I checked. Maybe there is for higher degree number fields, but I guess we don't have the technology yet for that. Hopefully soon.
Wonderful. Let's thank Ash again.